الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. طلاب الفرقة الرابعة شعبة الرياضيات إنجليش، نواصل محاضرات مقرر The Theory of Electromagnetic Fields. Now we are discussing the state of varying electromagnetic fields. This time we will represent two new concepts: an electric field produced from a variable magnetic field, and this concept resulted from the experimental research of Michael Faraday. The second concept is a magnetic field that arises from an electric field that varies with time. Faraday's law. Faraday declared if an electric current can produce a magnetic field, then the magnetic field must be able to produce an electric field. A magnetic field that varies with time produces an electric motive force. Electric motive force that creates a closed circuit current. Mathematical formula of this law is given as EMF equals minus dN by dt, where N is the total flux through the cross section of a magnetic circuit, and N equals the surface integral of B dot ds, where B the magnetic induction. And the electromotive force is the line integral E dot dl, where E is the electric field strength. In general, the electric motive force changes if the path shape changes. From 1 to 3, from equation 1 to 3, we find that line integral E dot dl equals minus d by dt surface integral of B dot ds. If the bus is static, then equation 4 becomes surface integral of nabla cos E dot ds equals minus partial B by partial T dot ds. Applying Stokes theorem, equation 5 takes the form EMF equals line integral of E L equals minus surface integral partial B by partial T dot ds. And since ds is arbitrary, then this relation becomes to Laplace cross E equals minus partial B by partial T. Equation 6 shows that the magnetic field changing plus time creates an electric field. Ampere's circular law. Ampere's circular law in case of magnetic fields that don't depend on time can be written as Nabla cross H equals J. Equation 9 is incorrect in case of magnetic field that varies with time, because equation 9 leads to Nabla cross H equals 0 equals Nabla to J, and this result Nabla dot J equals 0. This result conflicts with the equation of continuity Nabla J equals minus partial rho by partial T, and therefore we can put equation 9 in this form: Nabla cross H equals J G, and we try to find this term. Comparing this equation with the equation of continuity equation, we find Nabla dot G equals partial rho by partial T, and we use Nabla dot D equals rho and substitute here. We find the term G equals partial D by partial T, and therefore Ampere's circular law takes the following differential form: Nabla cross H equals J plus partial D by partial T. Maxwell's equations. We had previously taken two Maxwell's equations for time varying fields in the two equations. Nabla cross E equals minus partial B by partial T, and Nabla cross H equals J partial D by partial T, and the two following equations: Nabla dot D equals rho, Nabla B equals 0. These four equations, 13, 14, 15, 16, is called Maxwell's equation. We will now try to find the integral forms of the previous Maxwell equation 13 to 16 by integrating equation 13. We find that by integration equation 13 we find that the line integral E dot PL equals minus surface integral partial B by partial T dot ds. And by integrating equation 14, we find that line integral H dot PL equals I plus surface integral partial D by partial T dot ds. And equation 19. Equation 18 is called Ampere's circular law, and by integrating equation 15 we find that the volume integral nabla d dot nabla dot d tau equals the volume integral rho d2, and using the relation, the integral relation, the volume integral of this function equals the surface integral of d dot ds. Then we get the surface integral d dot ds equals the volume integral of rho d2. And integrating the equation 16 we find the surface integral p dot ds equal 0. And now when using electrostatic units to measure rho and vector d, e and j, as well as using electromagnetic units to measure the vectors h and b, Maxwell's equations for variable electromagnetic fields take the following differential forms. Nabla dot E equals 4 pi rho, nabla dot B equals 0, and nabla cross E equals minus 1 by C partial B by partial T, and nabla cross H equals 4 by A plus 1 by C partial D by partial T, where C is the speed of light in space. Electromagnetic potentials in Maxwell's equations. From the equation nabla dot B equation 22. From this equation nabla dot P equals 0, the vector of magnetic induction B can be placed in the formula. The solution of this equation is B equals nabla cross A, where A represents the vector potential, and substituting into equation 23 in this equation, substituting B equals nabla cross A, then we find nabla cross E equals minus 1 by C partial by partial T nabla cross E, and the solution of this equation can be written as E plus 1 by C partial A by partial T equals minus nabla minus 5. This electric field can be given as E equals minus 5 minus 1 by C partial A by partial T. Multiplying both sides of this scalar relationship by the operator nabla and using nabla d equal 4 by rho, and where d equals ke, we get nabla square phi plus 1 by c partial by partial t nabla dot a equals minus 4 by k rho. Where we assume here that a submedia is homogeneous, i.e. mu and k are constants. From Maxwell equations 24, this equation plus h and h equals b by mu, e equals ke. From Maxwell's equation 24, using the relationships, we get nabla cross A equals 4 by mu A plus mu K by C partial E by partial T. And by using the following vector identity on this side, nabla cross A equals grade nabla dot B dot A plus minus nabla square A, and substituting here and E, the electric field E from equation from equation 25 and substituting here, then equation 27, equation 27 becomes in this form: grade nabla A salib minus nabla square A equals 4 by mu A minus mu K by C grade partial phi by partial T minus mu K by C square partial 2A by partial T square, and we use this condition nabla A plus mu K by C partial phi by partial T equals 0, which is called equation of gauge invariance. Then equation 26 and 28, by using this condition, these two equations 26 and 28 become respectively into the following two forms: nabla square phi plus minus mu K by C square partial 2 phi partial T square equals minus 4 by K rho, and the second equation nabla square A minus mu K by C square by partial 2A by partial T square equals negative 4 by mu K. Equation 30 and equation 31 are the wave equations for the related scalar potential phi and the vector potential A. شكرا على الاستماع.